Hi, everybody. Just to start off, atmospheric and oceanic sciences, we can also be called meteorologists, but there's more to what we do than what you see on television in the weather forecast. My research has to do with high-impact weather processes. This is kind of fun stuff, in my view. And this picture right here shows a lot of interesting things. It shows a tornado, or a funnel cloud at this point, dropping down towards the ground, a rainbow, and some hailstones, which you can see in these very white objects falling from the sky. So this is a money picture, as we call it in our field. Specific processes that I care about are convective storms, like the one I just showed. And when you're underneath one, the sky is dark and it seems ominous. Some people get scared. But when you're far away from one and looking at it in the distance, it often looks like this, at least when they're developing. This is over cornfields where you can see them well. And another area that I'm very interested in is flows over mountains. And there's all sorts of dynamics that happen when air encounters a mountain. One thing that happens that's tremendously important for aviation, at least, is when the air passes over a mountain range. This is a very classic picture downwind of the Sierra Nevada. When the air passes over a mountain range, it forms waves that propagate deep into the atmosphere and ultimately break. When you're on a plane and you're flying over a mountain range, there's often turbulence. This is due to these waves. Down near the ground, this transport of strong winds from the upper atmosphere, it gets brought down towards the surface, and you get these tremendous winds. What often happens downstream of these windstorms is that the air is lifted up violently in what's called a hydraulic jump. And the hydraulic jump is accompanied by a rotor circulation. And you see that here, all this dust being picked up off the ground. It forms a cloud, you see, and when planes fly through this, they normally crash. So we have to know where these are happening to avoid that sort of outcome. So I'm trying to do two things. I'm trying to understand, or improve understanding and improve prediction. On the understanding side, they're closely linked, but they are two different areas. To try to understand these processes better, I use a variety of different techniques. One is observations. We have routine observations from satellites, from radars, from surface stations, radiosondes, and we also have intensive field campaigns, one of which I just took part in over this island of Dominica in the tropics. Horrible place to be. And we also use large eddy simulations, and these are simulations that use extremely fine resolution to capture the dynamics, the internal dynamics of clouds. And you can see these are clouds forming over a small hill. And what we're trying to do is to take all of this knowledge and turn it into analytical models, because these models can be used to further understanding, and they also can be used to inform prediction. To improve prediction, so prediction involves these big weather models run by Environment Canada and other weather centers. What I'm doing, my particular area, is probabilistic forecasting, and this involves running a set of forecasts, all with very similar initial conditions, but because the atmosphere is a chaotic place, they all diverge and go in different directions. And what we're trying to do is understand how much initial error we can tolerate in a forecast before it grows and diverges from reality. This is a thunderstorm that developed over the mountains of Germany in 2007 during a field campaign. And we ran a simulation of this event, and we can see that the maximum cloud top that was produced is all over the place. And where these clouds form was all over this mountain range. So we weren't able to, only some of the simulations were accurate in capturing this event. Okay, that's it. Thank you.